Hi guys, how are we doing? How's our day? How are we feeling about going to school? Oh, sorry. Anybody with me yet? Hi, how are you doing? You're back to school in like what, 2 weeks, right? What's the crack with you, Shag? Do you go back and have tests, or do you go back and it's a bit more chill? Test? Yeah, straight away. So it's the kind of making sure you like actually learn stuff over summer, aye? Or do you think is that the test you're going to do to get your predicted grades? I'm assuming you got your predicted grades before you left, but I can't remind if you said that you were already given your predicted grades, to be honest. They're just class tests. Grant, how are you feeling about them? What school do you go to? Can I ask? So we'll probably start in like a minute. Cronton, sick from Quaj. Where's Cronton? Is that England? London? I don't know. I don't know my little area of London, and that's it. Not very travelled. What's the crack with everybody else? What is that? What are you doing for your last 2 weeks of summer? In Warrington, which is England. I know that. Okay, so today we're going to do magnetic fields. So as soon as you get on, you should say hello, please. So I don't know if all of you are the same, hopefully you're the same people I've been teaching. But if you don't know me, again, I did sciences and math when I was your guys' age. And year 13, I actually found way easier than my GCSEs. So I guess it depends how you find managing your time. So when I was doing my GCSEs, it was just mad for me. There was way too many subjects. But for A-levels, for me, just subjects I liked, I found it a lot easier. And if you get anything from me, I highly recommend you do a sport. Because if you go home in the evening and all you've got to do is revise, you're never going to be efficient with revising. You're going to be bored stupid, right? So you got to have a sport or have a hobby that you can do most days. So when you do go home after school, you have like a bit of a break before you start to revise again. So I did rowing when I was your guys' age, and I rowed for like 20 hours a week, and I still managed to get A stars, right? And I do think rowing is the reason I got my A stars, because as soon as I finished after school, I went rowing and I came home. I only had a few hours to study, so I made sure they were efficient. So if you get anything from me for next year, I'd highly recommend joining a club or join a sport. And if you don't believe me, there's actually loads of research that the more sports you do, the greater capacity you have in your frontal lobes for retaining information, right? So sports does go hand in hand with knowledge. But run over. Okay, so do you want to give it a go? How would you draw the dipole field around a bar magnet? If you can maybe draw on your work pack if you've got a chance to print it, or just draw on a piece of paper, or hopefully you can write it in the chat. And how do magnetic field lines differ from electric or gravitational field lines? So I know I've got more here than Ishak, so say hello to me, give me a shout. JMB, hello, thank you for saying hello. Nalia, hi. Thank you for saying hi. Ethan, hello, hello. It's nice, yeah. Thank you for saying hello. It makes me feel a little bit less alone here, eh? Oh, I want to say Soham. You told me how to pronounce your name last time and I completely forgot, sorry. Celine, hello. Was it Soham? Did I get that wrong again? Sorry if I did. Soham, sorry. Ah, JB, you know, thank you. So do you all start in 2 weeks, aye, for September? Do you guys know each other, JMB and Soham, or just bond over these lessons? Okay, so what about a dipole field around a bar magnet? What would you draw? That's like something you did, hopefully in Key Stage 3 and GCSE. You just bond it online in it. Oh, that's really good. Well, hopefully that means that kind of shows you what the lessons were like for the year, right? And I will have learned your names by then. None of you go to the same school then, no? Or what's your physics teachers like? The young, the old, the man, the woman, the English, the not? Do you like them? Do they like you? Or if you don't want to tell me your crack, you can tell me how to draw the dipole around a bar magnet. So for example, how would you draw the field lines around a bar magnet? Your physics teacher's cool, to be fair. What makes them cool? My physics teacher in high school was cool. I really liked him. He's called Mr. Arnold. Shy Mr. Arnold. Not that I ever see this, but anyway. Yeah, from north to south, lovely. Okay, so we have a magnet from Key Stage 3. We already know you've got North Pole, you've got a South Pole on a permanent magnet. The way I learned it is Santa Claus lives in the North Pole, so it's come out of the North Pole and then he has to go around the world to deliver his presents. So he goes out of the North Pole and he goes around the world to deliver his presents, so then he has to go into the South Pole. Okay, so that's what dipole means. So dipole, like dice is 2, so dipole is just 2 poles. Okay? Okay, next one. What do you think magnetic field lines show us? So what do the magnetic field lines show us? So remember we did gravitational field lines show us the direction that a test mass would move. So we dropped a mass there, we show of 1 kilogram, we saw way it would move down towards the surface of the Earth. Electric field lines said shows the direction of a positive test charge would move. So remember we said if we got a positive plate here, got a negative plate here, that would go from the positive to the negative. And then magnetic field lines then always just show us the way that a north pole would move, right? So it always goes out of the north and into south. So magnetic field lines always go from north into south. So exactly what JMB said. Okay, what about a wire? Do you remember this from GCSE? So if I have a wire and there's my current, what does the magnetic field line look like around it? Do you remember from GCSE? So this is probably a bit of recap, trying to bring back some learning from GCSE. There's a hand that helps you remember the rule. So run a current carrying wire. So I've got current moving through my wire, curls around. Thank you, JMB. Right, love it, yes. Yeah, even, thank you, yes. So use your right hand to find the current. Your thumb always shows you the direction of the current, and the way that your fingers curl show you the direction of those magnetic field lines, okay? So clearly here, if I've got current going up the board and I put my thumb up, because my fingers are curling towards my face, that means magnetic field lines are curling around the wire, okay? So those are my magnetic field lines around my wire. And we know it gets weaker further away from the wire because the field lines are less dense further away from the wire, okay? So we all know that wires have magnetic fields around them, and it's the circular. Okay, so why then is there a force on a wire? So say we take our wire now, so it's not going up now, our current's going down. Why is there a force on this wire when we put it inside the magnetic field? So why is there a force on the wire when we put inside a magnetic field? And what are 3 ways that we can make it increase that force? So how come, hint is what we just did here, how come we put this wire inside this magnetic field, experience of force? And what was 3 ways to increase it? It was 3 ways to increase it. Tell me what you think. Do you remember from GCSE when you did about transformers? Because of the induced magnetic field due to the moving charge and wire, this interaction of fields. Yeah, thank you. Good job, JB. Lovely. And then in the chat, can we just have a go at 3 ways to make it stronger? So what JB says, when we have our thumb, now our thumb's going down, my fingers are curling away from me. So my fingers are curling away from me, so the current is going in this direction around the wire. Except what JB says, we have 2 magnetic field lines now that are crossing each other. So because we have 2 magnetic field lines across each other, that's why we experience the force. And there's 3 ways to make this force stronger. Yeah, thank you, Ethan, good job. Another one thing we could do is that we can increase the current, right? We make the current really high because we could add more batteries. So that's something we could do. Or other ways that, yeah, good job. The equation that we use then is F equals BIL. We're gonna look at a new equation today. So F equals BIL, so that's what we did in GCSE. So that's from Fleming's left-hand rule. So from Fleming's left-hand rule that we're gonna practice today, we saw there's gonna be a force in the wire due to a magnetic field, a current, and the length of wire, as long as they're perpendicular to each other. So hopefully you're thinking one thing we can do is increase the current. Hopefully you're thinking another thing we could do is we make our magnet stronger, right? We can use a stronger magnet. And maybe remember anything else? Longer wire, good job, a longer wire in the field. And the way that we make a longer wire in the field, do you remember what you call it when you coil a wire? Do you remember that? So instead if we take the wire, so I have my wire around this microphone right now, I know there's a magnetic field around it. If I want to make it stronger, I can coil the wire, thank you, I can coil the wire up, and that's going to make a solenoid. Okay, so that's your stuff from your GCSEs. So we're just going to quickly recap that again. Okay, so again, what we just said here is clearly magnetic field lines, yeah, solenoid, thank you, improps. So magnetic field lines, they always come out of the North Pole, because Santa Claus lives in the North Pole, it's come out of the North Pole, it has to go around the world to deliver his presents. So they always go into the South Pole. And we know what the field lines look like because we can drop iron filings. Yeah, solenoid, thank you, Michaela. So we can drop iron filings. So remember, iron filings, iron is an induced magnet. That means it can become magnetic. So if you drop all these iron filings around the magnet, we can see the shape of the field lines. And that's how we know it's strongest at the poles because there's more dense field lines. Okay, the other stuff we just talked about there, we talked about if I've got a wire and I've got current flowing through it, we use our right hand here, okay? So if you use our right hand, the current's going up. You can see your fingers curl around the wire. I don't know my right from my left at all there. Oh my goodness, I've been using my left hand, sorry. Right hand's going up, so my fingers are curling towards my face. So because my fingers are curling towards my face, that's why it's going in this direction. You're probably thinking that last slide, what was I doing then? That doesn't make any sense. I used the wrong hand, sorry. I think it was you guys I told when I did my driving test, I had it right and left on my hand. That's where I'm at. So that was a terrible picture of my right hand. There's my thumb. My thumb's up. My fingers are clearly curling in this direction, not the other way. What was I doing? So then if I have current and it's going up the way, because my fingers are curling in that direction, that's why it's going this direction around the wire. And in my other image, when the thumb is going down, my fingers are curling around the other direction. So I had that going the wrong way around there too, sorry. It should have been going round in this direction, right? So clearly right and left matters. Okay, so what we're saying here is current is for our right hand, so our thumb goes up, shows the current, and my fingers are curling towards my face, which is why I know the direction of those field lines. It's going towards my face, so I can see the curve of those field lines around that wire. We know it gets weaker further and further away from the wire because they're less dense, okay? We just talked about a solenoid. A solenoid, remember, J and B there said that we want to make the wire longer, right? So a way to make the wire longer inside the field is just to coil it up, right, to wrap it up. So that's all we do is we have a long wire. To get more of it in the field, all we do is wrap it up in a coil. When I wrap up my coil, that's how I can get more wire, more length of wire in that space. Okay, and then other things you might have seen, hopefully, from your GCSEs, but if you didn't, you look at it now. The way we look at it is if it's an end shape, you do the wheel arrow, so south, end. So south, you do your arrows in the end, north, you do the arrows in the end. So if it's going in this direction, the solenoid, that's how you know it's a south pole. It's going in that direction in the solenoid, you know it's a north pole, okay? So we look at our field lines because they're going in this direction here. So we look at it's going in that direction here, it's going to be my south pole. So we figure out the poles of our solenoid. Okay, other things we talked about there is we talked about how come when we put a wire inside the field, the magnet, experience a force. and exactly what we said above, because they are going to interact with each other. So again, we said we've got our circular magnetic field lines around our wire, and we have our uniform magnetic field lines, which are a magnet, and we place that wire inside the magnet. You can see that on top, they're going to add together. That's why we get stronger on top. If you look at the bottom, here they're all going in this direction, and here they're going in the opposite direction. So those two vectors there will cancel, and that's why you don't see any field lines below, okay? So that's why the wire then experiences a force because of those directions of those field lines. Yeah, when you coil it up, you get a stronger field because you got a lot more wire inside that field. Okay, then Fleming's left-hand rule. The way I remember it is exactly what the equation with J and B said. F equals BIL. So to me, F is the first thing, so that's my thumb, right? So left hand, right, left, yes. F is the first thing, so the first thing is my thumb. B is the next letter, so my next finger is B. And then I is your next finger. So that's going to be your middle finger, and that's going to be the middle finger, which is I. Okay, so it's going to show us the direction of magnetic field line. So F, B, I. It's always in that direction. Okay, so F, B, I. Thumb, magnetic field lines, current. Okay, and does anyone remember what way current has to go? From the chat, what way does current have to go? Do we always go from positive towards negative, or do we always go from negative towards positive? What way does the current have to be? So what I'm trying to ask you, like for magnetic field lines, we know it has to go from north to south. But what about current? What is the direction? Yeah, thank you, JMB, good job. Big important point here is it's always conventional current, okay? So conventional current, if we have our wire, conventional current, remember, is what we draw on the picture. So it comes out of the positive and it goes round into the negative, okay? So that's the direction of the current here, out of the positive and round into the negative, okay? So the conventional current is this one. We're looking for from positive to negative. That's the direction we use. Okay, just to practice, F equals BIL. Can you please tell me the magnitude of the force? Hopefully it's just a nice bit of math to like wake these up. So pop in the chat, what's the force here on this length of wire? So we're told it's 5 meters. We're told the current. We're told the magnetic field strength, which is in Teslas. What is the force? You can pop in the chat. What's the force? Improp says 8.4. Do we agree, disagree? And thank you for being first to give a go at it, Improps. We get a unit in there though. J&B agrees, lovely. What happened to Celine and everyone? Come on, help me out here, people. J&B is holding it strong here. So yeah, Newton's, good job. What about everybody else? Do we agree? Do we disagree? Hopefully we're thinking. B is our magnetic field strength. Thank you, Ethan. Is magnetic field strength is measured in Teslas. So it's going to be 120 milliteslas. Remember that's times 10 to the negative 3. Multiplied by I, which is my current. Which the current is 14 amps. And we're going to multiply it by L, the length of wire. And the length of wire here is 5 meters. So we multiply those all together. Yeah, Nalia, beautiful. Celine, beautiful. Lovely. Static spark, 8.4, beautiful. Lovely, 8.4 newtons, nice. JMB, as you can see, I don't know my left and rights, or can I spell? So we're not going to blame you for a few spelling mistakes either. Mikhail, beautiful, 8.4 newtons, nice. Okay, so that's using F equals BIL. Okay, so now we're just going to practice using Fleming's left-hand rule because I just want to make sure we're good from the GCSE stuff before we push on with the year 13 stuff, okay? So hopefully you've seen this in your GCSEs, but if you did combined, you probably didn't. Probably only seen you did triple, okay? So the way that we can draw magnetic field lines, and sometimes they'll do this on your test, is they'll represent them by a circle, okay? If a circle has got an X through it, they're telling you the magnetic field is going into the page. And if it's got a dot in the middle, it's telling you the current is going, or the magnetic field is going out of the page, okay? The way I remember it is I think about an arrow, okay? So like, if you think about an arrow, the tip of the arrow is just like a point. So the arrow is coming towards me, I would just see a point. So something coming out of the page or towards me is going to be a point. And if the arrow is flying away from me, I see the back end of the arrow, okay? That back end of the arrow then means it's like the X, okay? So clearly we all know up and down, left and right is really easy to draw. But if you're trying to represent someone coming out of your test paper or into your test paper, that's when they'll give you these shapes, Okay, so if the arrow is flying towards me, it looks like the tip of the arrow coming towards me, which is why we just see that little point. And if the arrow is moving away from me, I see the back end of that arrow, and that's why you see the X. Okay? Okay, so to practice it, what is the direction of the missing component? Can you pop in the chat? So what is the direction of the missing component? Pop in the chat. So hopefully you're thinking left hand. So JMB says into the page. Do we agree? Nalia says into the page. So our magnetic field is going into the page. So the missing component can also go into the page. Because remember, Fleming's left-hand rule, we have everything at right angles to each other. Okay, so two things can't go in the same direction. So remember, first thing we have is force, then we've got our magnetic field, which must go from north to south, and then we have our current that we just said had to be conventional current, so going from positive towards negative. Okay, so now I'm getting down. What do you think? So magnetic field is going into the screen. So B, you want to point into the screen or into your page. And my current is going towards the right. Okay, so again, what we should hopefully do if you're left hand, right, left, is magnetic field. My magnetic field is going into my screen. My current is going towards the right. So my right, yeah, Ethan, good job. So your thumb, hopefully you're figuring out your thumb is your force. Your force is going to be going up. Okay, so I'm just check that. So again, Fleming's left-hand rule, give someone a thumbs up, then you put your first finger out like a gun. Say like FBI, right? FBI, gun. So FBI, force, magnetic field, and then your next finger, you have to make sure it always stays at right angles to that first finger. Okay, so it's quite hard to do the first few times because you've got to lock your hands and then you keep your elbow loose. So it's your elbow you move about when you're changing things around, but you keep your fingers locked. Okay, so just make sure, can we give me a plus if everyone got force up in the chat so I know we're good to move on? We're going to practice it a few times, but make sure we got force, it's going up. So again, FBI, my magnetic field is going into the screen or into your page. The current is going towards the right, so hopefully everyone has their thumb then pointing up. Yeah, thank you, honey, Honain, is that right? Sorry, I was wrong. Thank you, Ethan, thank you, Nalia, JB, yeah, happy days. Celine, beautiful, lovely. Okay, next one. Omar, thank you. Oh, hello, Omar. So this one, what is the missing component? So I've got magnetic fields coming out this time because it's like the arrow coming towards me. And the current this time is going towards the left. So thank you, Mikhail. So what way is the force going this time? Up, down, left, right, into or out of the page. Up, down, left, right, or into or out of the page. So hopefully you're thinking, remember Fleming's left-hand rule, F, B, I. So Ethan says up, force is going up. Do we agree? Do we disagree? So if you're in left-hand rule, F, B, I. My magnetic field now is coming out of the screen. So I've got to turn my hand, but not change my fingers. Just rotate my elbows so my current is going out of the screen. Whoops, out of the screen. My current is going towards my left. So I look at where my thumb is going, and my thumb is going up. Right, so that's how I know it's going up. Yep, JMB, good. Ethan, we're good. So clearly our force here is going up. Okay, right, next one. Right, see if we can get 7 more people in the chat before Ethan does his time, because Ethan's got it now. Michaela, up, good job. Okay, what about this one? So I've got current is coming out of the board, so that makes sense. My tip of my arrow is coming towards me, and my magnetic field is going down. Okay, so what way is the force going? So remember, it's F, B, I. So FBI. So I'm trying to figure out where the force is going. I've got my current is this finger. It's coming out of the board. And my magnetic field, I have to rotate my hand, so my magnetic field is going down the way. So what way is your force going? Pop in the chat. So again, remember, keep your fingers locked. You just rotate your arm. Rotate your arm. Yes, yes, perfect, good job, right? Yes, thank you, Nalia. Priscilla, good on you, thank you. Go to the right. Yes, fab, good job. Yeah, brilliant. Because again, we've got current, which is this finger, it's coming out the board. My field is going down the board, so my thumb is going towards my right. Yeah, Omar, beautiful. Yeah, Ishak, good job. Okay, what about this one? So our force now is going towards the left, and I have the field going down. So what I'm asking now is, where is the current going? So where is the current going? Okay, lovely. So remember, F is my thumb, B is my next finger, and then I is my next finger. So I've got force going towards the left. Ethan, good job. Yeah, Ishak, beautiful. I got force going towards the left. My field isn't going up, my field is going down. So I have to rotate my hand to get my field to go down, but my force to go to my left. And then hopefully you figure out your current is pointing in, yeah, good job. Yeah, you see me try to do there? So the current is going to go into the board or into the screen, or if it's your exam, you would write into the page. And they do ask you this stuff. So you don't have one marker, but they will ask you what direction things are going. Okay? Yeah, beautiful. Right, easy. Okay, what about this one? So the current is going into the page. The field is also going into the page, right? Because it's the back of the arrow. What way is the force going? Or what is the force? On the chat. So obviously the back of the arrow, so the current is going into the board. The field is going into the board. What do you know about the force? From the chat. It's not down. This is maybe a bit of a trick question. No force, Ethan. Good job. Yes, happy days. So the force is going to be 0, because remember we said at the start, they all have to be at right angles to each other. So the only way for our current, the only way for our wire, our current in the wire to feel a force is if they're perpendicular to each other, okay? So sometimes your wire might be at a slight angle, but because we can resolve it, we can find out what that perpendicular component is. And it's only the perpendicular component that will ever feel force, right? Because they have to be at right angles to each other. Yeah, Michaela, beautiful. Yes, nice, good job. Okay, so now we're going to just practice a bit of math with it. So it says, draw on the section of the wire between the magnets, the direction of the current, and the magnetic field pattern produced by the wire. So maybe just write it in chat. So right here, what way is the current going? And then right here, what way is the magnetic field going? So up, down, left or right, or into or out of the board. So which one is it? What way is the current going in that little red box? And what way is the magnetic field going in that little box? What way is the current going and what way is the magnetic field going in that little box? Yeah, good job. So nice. So remember, the way I remember it is the positive, negative. Positive's got more lines, so positive's always the longer side. So remember, the current comes out of the positive side. So what's happening here is through that little section of the wire, the current is going down because then it goes back towards the cell. Yeah. So for this little section, we've got the current going down. Just going to rub that out so we can draw it a bit better. So our current is going down here. And we know that the magnetic field has to go from north to south. That's the direction of our magnetic field. Okay, so what direction will be the force on that wire then? Keep up in the chat. What's the direction of the force on that wire? So we just drew on that the current in that little section is going down, and we know the magnetic field in that little section is going towards the right. What would be the force on that wire? Up, down, left or right, into or out of the page. Up, down, left or right, or into or out of the page. Yeah, out of the page, that's how you say it. Yeah, good job. So you're going to say out of the page. Yeah, even Priscilla, beautiful. It's going to go out of the page, right? Because I use Fleming's left-hand rule. F, B, I. So because we got our magnetic field is going towards the right, so FBI, magnetic field, is going towards the right. The current is conventional current. My current is going down, so my thumb is coming out of the screen or out of the board or out of your page. Yeah, nice, out of the page. Nice, perfect, Nadia, in props tomorrow, beautiful. Okay, we know, we just talked about this one quite a lot, we know there's a force in the wire because the wire will have its own magnetic field because of our right hand rule. So my fingers be curling towards me here. So the right hand rule shows us that there is a current flowing through that wire. That wire has its own magnetic field, and that magnetic field interacts with the magnetic field between the permanent magnets, and that's why I experience force. So now, can you tell me what the length of the wire is there? So remember our equation from GCSEs is F equals BIL. So I'm giving you the force, I've given you the current, I've given you the magnetic field. What is the length? What is the length? So put in the chat, what's the length of the wire? Don't forget about your milliteslas. So don't forget about your milliteslas. So what we're thinking, 0.04 equals 50 times 10 to the negative 3 times by 15 times by some length. Yep, improps, Nalia. Yep, lovely. 0.053, and then our unit would be, hopefully we're good. Yep, Nalia, Priscilla, Omar, beautiful. And then meters, right? So our length for our is in meters. Okay? Yeah, so fab. Celine, beautiful. Yeah, nice. And then the last one's, which law states there must be an equal but opposite force in the magnets? Yep, Omar, thank you, meters. So we know that Newton's third law, so Newton's third law tells us that if there's a force on that wire, there's also going to be an equal but opposite force. The magnet exerts a force on the wire exerts an equal but opposite force on the magnets. Okay, because of Newton's third law. Yep, Michaela, beautiful. Okay, so that's kind of like recapping the GCSE stuff. Now we're going to get on to a bit more of the A-level stuff. Okay, so this is a required practical. So the required practicals, all come up on paper 3. Okay, so paper 3, section A, is where all the required practicals come up. So I took a snippet of this from a past paper. So it says, if the reading on the scale increases by 120 grams, what is the direction and the magnitude of the magnetic flux density on the magnet? Okay, so see if we can give it a go in the chat based on what we just learned in that last slide. So it says, the reading on the scale increases by 120 grams. So for example, when the switch is open, there was a reading on the scale. And when we close the switch, this number went up by 120 grams. So if the number in the scales went up by 120 grams, what do you know about the direction of the magnetic field? So I want to know the side that I shade in, is that a north pole or is that a south pole? So the side that I'm shading in, is that a north pole or is that a south pole? So J and B, you're right that you figured out the force must be acting down. So the force is down, but I want to know the direction of the magnetic flux density. So nice, hopefully everyone figured that as well, right? So if the reading on the scale has went up, that must mean there's a bigger weight on the scale. So that must mean there must be a force going down, so there's a bigger weight on the scale because our wire is free, right? Our wire is free, it's not clamped. There's a bigger, when we put the current, we close our switch and we have current flowing through this wire, because there's a magnetic field through the wire and there's a magnetic field in the magnet, they interact with each other to create a force that's going down. So if I know the force is going down, this shaded side there, is that my north pole or is that my south pole? Yeah, we know the current, good job. We do know the direction of the current because look here. So look here at the cells, figure out what way the current is flowing that wire. And then figure out, is that shaded side going to be a north pole or is that shaded side a south pole? So is the shaded side a north pole or is the shaded side south pole? North, do we agree? So Ethan says it's going to be a north pole. Do we agree? So hopefully we're thinking, there's my longer side, that's my positive. So conventional current is what matters here. So in this section of the wire, the current is going towards the right. So when I do Fleming's left-hand rule, so FBI, clearly we just said the force is going down. So force has to be going down. And our current, we know, is going towards the right. So I'm trying to figure out what way does that mean that my magnetic field is going. So take my left hand, I said my force is going down. FBI, my current was going towards the right. So hopefully everyone figured out the magnetic field then is coming out of the board. So, magnetic field must be coming out of the board, okay, or like towards us. And we know magnetic field has to go from north to south. So the way for it to come out of the board is exactly what Ethan said there. Yeah, fab, and what J and B said. That must be my north and that must be my south because I want my magnetic field lines to come out of the board, like towards me. Yeah, so imagine this was like a 3D setup. they'd be going towards us, those magnetic field lines. Okay, so another student set this up, but this time they only get 115 grams. So they're supposed to get 120, but they got 115. Pop in the chat, why do you think that is? So that might be something that comes up in a practical paper for you. You're trying to figure out what, when they do this experiment, why did they only get 115 and not 120? How do you think they set it up differently? So we're practicing some practical knowledge paper free stuff now. This is a required practical. So if another kid set it up and they got 115 grams, you're trying to think through, what do you think they might have done differently that they got a lower number on the scale? So they got, basically what we're saying is there's a less force here. So why would they got a less force? Oh, so you're thinking about the variable resistor. Okay, let's keep going with that one. A zero error. Yeah, actually, I'll take that one too. Yeah, Ethan, yeah, I was trying to think without gate marks. Yeah, good job. It could be a zero error. So instead of the scale saying 0 when they started using it, it could have said 5 grams when they started using it. Yeah, so it could have been a 0 error. Yeah. Let's say though that all the equipment, I want you to think more about the wire. What might be wrong with the wire? You said, what was it, variable resistor, a different value. How would that affect it? So if their variable resistor was a lower value, that's a good point for you, but you need to like push that one a bit more. Why would changing the variable resistance make me have a lower force? Okay, so we know V equals IR. So if we want to have what you're saying a lower current. If the current is going lower, that's because we've made the resistance higher. So if they've used too high of a resistance, that means their current is going to be lower. And because we know F equals BIL, if the current is lower, the force might be lower. So yeah, that's a good point. So that's a nice one, but you need to talk it through like that if you see that JMB. So you can't just say change the variable resistor. You might say, oh, they might have used too high of resistance, so their current was much lower. And because we know F equals BIL, if the current is much lower, they got a much lower force. Okay, yeah, they might have had a higher temperature. So a higher temperature, if we wanted to push that one, a higher temperature might be because they didn't use the switch. So hopefully you guys know when you're doing practicals, what you should be doing is turning on and off the switch between your readings, because you want to make sure, like you just said there, Omar, the wires don't heat up. So you can say maybe the wire became too hot, which means there's much higher resistance because they didn't use the switch. They didn't allow the wire to cool down before they used it again. That's nice. Hi, Eddie. So what I was thinking about this one, I don't know if you got it, but it might be, and probably the most likely one is, and this is something you have to do when you're doing this practical. Remember we said everything has to be at right angles? So if this wire here isn't perfectly at right angles to the magnet, so for magnets from north to south, if that wire, instead of it being perfect at right angles, let's say the person has it shifted slightly off here, because remember, there is still a component, if we resolve that orange into its horizontal and its vertical, there is still a component that is right angles to my magnetic field, but not the whole wire is. So one of the main reasons was because they didn't ensure that the wire is perpendicular. And the way that we ensure things are perpendicular is by using those set squares. Do we all know what a set square is? So remember, like a set square, you would place to make sure that things are right angles to each other. So a set square, like in your little math set, so these in your math set, they're tiny, but you can get much, much bigger ones to ensure that things are always at right angles. Okay? Okay, so I'm just gonna rub out this circle so we can see the next one. Number 3 then, so I'm gonna change colors. Sorry. Oh, now I'm panicking. Where are we at? Yeah, sorry. Okay, number 3 then says that a third student got a number to be, instead of increased by 120, they got the number to decrease by 120. What do you think that person's done? So instead of the number going up by 120, this person's number has went down by 120. So what did they do differently? What might have they done differently? Give me your ideas in the chat, because your ideas are good. We just need to push them a little bit more. Switched the good old terminals. The good old terminals. Yeah, that's a good point. Nice. So nice you notice what JMB said, Clearly, if the number has went down, that must mean the force isn't going down anymore. The force is going up. So the only way the forces went up is because they changed the direction of something. Yeah, nice job. So what they've done here is they've probably put the cells around a different way. So they put the cells a different way. So instead of the current going that direction, the current is going the opposite direction. Yeah, good job. And they could have turned the magnet around. So instead of that being a north and that a south, they might have turned it that's the north and that's the south. Yeah, good job, right? So the only reason the force would switch direction is because either we switch the direction of the current or we switch the direction of the magnetic field lines. Yeah, nice. Okay, next one is just trying a bit of math again. Okay, so this time we're going to use F equals BQV. So just so you see, in GCSE you used F equals BIL. So the force is B, your magnetic field strength, times the current times the length of the wire. Okay, but just to show you where this equation comes from. So hopefully everyone's okay that speed, so speed equals distance divided by time. Okay. So instead of writing distance, I can write speed times time. So instead of writing F equals BIL, I can write F equals BI. Instead of writing L, I can write speed times time, right? And then we also know Q equals IT. We know that from GCSEs. So instead of writing I times T, that's where that equation came from. F equals B, Q, V. Okay? So BIL is what we have in our GCSEs. But because we know speed is distance divided by time, distance is going to be speed times time. So instead of writing length, I can just pop in there speed times time. So instead of writing length, I popped in here speed times time. Because I know charge is current times time, if I've got a current times a time, I can get rid of that and just write a charge. Okay? So this is the main equation you'll be using this topic, F equals BQV, and it's on your data sheet, okay? So you don't remember it, but you will remember it by the time you do this topic because you do it so many times. Okay, so first question says here that I've got an electron enters a uniform magnetic field. So there's the speed of my electron, that's the velocity. The electron is heading downwards and our magnetic field is 200 milliteslas and it's going into the page. So here I can clearly see magnetic field, there's the tip of my arrow, is not going into the page. Sorry, that should have been X, that's my bad. I apologize. There, now it's going into the page. Okay, so what is the direction of the force on the electron? Can you pop in the chat? What's the direction of the force on the electron? So Ethan says to the right, do we agree? Remember, Fleming's left-hand rule, F, B, I. So magnetic field is going into the board or into the page. Current, remember, is conventional current. I think that's where we went wrong. So remember what conventional current is. Remember, conventional current means it went out of the positive and it goes around into the negative. So it goes from positive to negative. So current is not going down. Does everyone see that? The current is actually going up. Okay, because remember, it's the way the positive moves. Our negative is moving down, so our current is actually going up because it has to be conventional current. Even, yeah, we got that there? Yeah, I'm glad we got it. Does everyone else see that? They do this quite a bit as well, okay? So just make sure we're good. We know that actually, if I have a perfect circuit here again for everybody else, there's my negative terminal. We know electrons actually want to come out of a negative terminal and they would move around to the positive, right? But conventional current isn't shown as the way electrons want to move. Conventional current we draw on the diagram from the positive round to the negative. So everyone see that conventional current is the opposite to the way that the electrons are going. So if the electrons are going down, that's the way the negative is going. The positive or conventional current is actually going up. Okay, so my B is going into the board and my current is going up. So it even says left. Do we agree, disagree? So F is BIL. So FB, B is going into my page. I, my conventional current is going up. Okay, it's a conventional current. So the force in that electron is actually going towards what even said their end, actually going to the left. Okay, so that electron, it's moving down and there's going to be a force on it trying to push it towards the left. Yeah. Can you give me a plus if that's good? If the other people haven't answered yet, just make sure we're okay with that, because it has to be conventional current from the positive to the negative. It has to be conventional current from the positive to the negative. Yeah, Ethan, thank you. Everyone else, are we happy? Or tell me we're not happy. So if we are happy, can you now tell me what is the force? Yeah, Omar, thank you. If we are happy, what is the force now on that electron? Yeah, GMB, thank you. So what's the force on that electron? So we're using F equals BQV. We were given the magnetic field, 200 milliteslas. So 200 times 10 to the negative 3 times by Q. Do we know what the charge of electron is? If you don't know, you've got a data sheet, right? But I kind of figured you probably would know because you do it so many times. You'll definitely know it by the end of the year. You're so close, Nalia. Is that your final answer? Your final answer is perfect, Nalia. Yes, sorry, I thought you were telling me the charge. Yeah, brilliant. Charge of an electron is 1.6 times 10 to the negative 19. Then you multiply by the velocity, which is 5 times 10 to the power 6, and you should get a final answer for force, which is what Nalia said, which is perfect. 1.6 times 10 to negative 13 newtons. Yeah, Nalia, lovely. Just pop in your unit for us there and help us out. But yeah, that's perfect. So hopefully we just did what Nalia did. You were fast, that was brilliant. So what Nalia did, yeah, Michaela, beautiful. 1.6 times 10 to the negative 13 newtons. Nice. Nice. Okay, for this one then, what is the motion of the electron in the field? Hopefully you can see if the electron wants to move this way and the force is move right angles. Does anyone know what motion that will start to cause? What way will it move? Think about things that you've learned about in topic 1, paper 1. If the force is at right angles to the speed or the linear speed, what motion normally are we looking at? Do you remember? When we've got things, their speed is at right angles to the force. Yeah, circular, thank you. Yeah, brilliant, circular. So this topic starts to bring in circular motion, okay? So we know from circular motion, remember paper 1, F equals ma. Instead of writing acceleration, we can use F equals mv squared over r, or F equals mw squared times by r. Okay, so there's 2 equations from paper 1 that you're going to start to use now in these topics, okay? So remember, v is our linear speed, and then if you remember w is the angle we sweep out in a certain time. And if it's a full circle, that angle is 360 or 2 pi. And if it's a full circle, we use the period. So that's why it's a capital T. Okay, so that's what W is. Okay, so what we're going to look now is we're going to start learning what a cyclotron is. Has everyone ever seen a cyclotron? Or know what they are? Or know where a big one is that's really important? So my uni, so I went to Michigan State University in America, and they all knew, yeah, the particle accelerators, yeah, good job. The coach who was trying to recruit me for rowing knew that I was into physics, and no UK universities can have it on their campus because we don't have, America's just like triple, like way bigger than the UK, obviously, not triple size, but like probably like 52 times the size, right? The UK is not even the size of a state. But the university I went to, they had cyclotrons in the campus. So I don't know if you've heard about Michigan State University, but they're really good for research into particle physics, or like nuclear physics. So they have their own cyclotrons on campus, which is amazing to think about, right? Because I know we have ones in Switzerland and we have ones in Europe, but we don't have any that's joined to a university that a student could just go. So anyway, cyclotrons is what our particle accelerators are, right? And the reason you want a cyclotron, not sure that's like a feasible amount of money, but if you go to a university that has one, maybe. So yeah, what cyclotrons do is they speed the electrons up to really high energies, and then normally we speed them up, and then we try to get them to collide, okay? Because we want to get electrons and really particles collide, because then we want to observe the effects of them. There's a series on that a few people here watched at work about cyclotrons and the Large Hadron Colliders around the world. Do you know what series I'm talking about? I want to say it was on Amazon, or was it Netflix? And it was all about physics and aliens were trying to destroy physics on Earth. Holika here told me about it. And I've completely blanked it now. Does anyone know what I'm talking about? It was like a show about aliens coming and they're trying to destroy physics. so that when they come, primer, no, I don't think it was primer. I'm gonna find the name of it, and then you're all gonna have to watch it. I'm gonna Google it while you guys are doing this math. Yeah, I'm gonna Google it when we're doing the next bit of math, because now I feel I've just wasted time. Okay, so I'm going to talk through the cyclotron, and then so I'm going to talk through these 3 questions. So these are 3 questions. I just want to put them up so you can see what type of things would come up in exam. And then after we talk through it, you're going to try this math. Okay. So what a cyclotron is here you've got a source of protons. Okay. So my source of protons, free body problem. Zoya or Can, yes, beautiful, thank you. That's what. Yeah, you saved me a lot of time trying to Google it. Yeah, please, everyone, I highly recommend if you're looking for something to watch. What was it on? Was it Netflix or Prime? I don't remember. Free body problem. Yeah, Holika here told me to watch it. It's actually great. So free body problem. So it's all about like physics. There's the first few episodes are all about how the cyclotrons and the Large Hadron Collider stopped working on Earth. It was on Netflix. Yeah, it's all about how they stopped working on Earth, and like all these scientists start committing suicide because they're basically going crazy. That's very good. That's very good. I like it. Thank you, Zoe. You saved me there, because I was you know when your head hurts and you're trying to think about a name but you can't get it. So yeah, cyclotrons. So what happens is you have protons, so the protons come out, okay, and then do you see here you've got a high frequency alternating voltage. So what that means is we know one side's going to be positive and one side's going to be negative, right? So if I have a proton and it comes out here and it moves across, let's say it gets to this point here, my proton's positive, this D, so we call them Ds, because it's basically the shape of a D, this D is negatively charged, so the proton gets accelerated from the positive, the proton gets accelerated from the positive side over to that negative D, okay? So as soon as that proton gets accelerated across that gap, because we know E equals VQ, energy is voltage times charge, that proton is gaining energy, okay? And we know kinetic energy then is 1/2 of mv squared. So because it's gaining energy, it's gaining kinetic energy, the speed of that proton increases. So now my proton's here, right? It's inside the negative D. But then the voltage will switch, because it alternates, it changes, so this side becomes negative and this side becomes positive. So when my proton travels around and gets here, positive proton, because the voltage switched the polarity of the D's around, now that positive proton will get accelerated across again into the negative D. And then that positive proton will travel around this D, and once it gets to here, the polarity switches again for this one now to be negative and this one to be positive, so my proton gets accelerated across the gap again. So hopefully you can see every time we go across a gap, the proton keeps getting accelerated, it keeps increasing energy, so its speed keeps increasing across the gaps, okay? But clearly we can see as the speed increases, it goes through a circular motion. And it goes through circular motion because we've got a magnetic field across the whole D's, okay? So we've got a magnetic field here across the whole D's, and the magnetic field makes it move in a circular motion. So my proton, if we look at it, if my proton's here, moving in that direction, that's the direction of my current because it's positive, and we know there's a force on it pulling towards the center. So if I do my Fleming's left-hand rule, and I have FBI, if I have my current at this point moving in that direction and the force going towards the center, hopefully everyone can see the magnetic field here is moving up. So there's a magnetic field that's moving up through this D the whole time, a uniform magnetic field, okay? So explain why the proton undergoes circular motion inside the D's is because there is a uniform magnetic field. Hi, Chatterjee. There's a uniform magnetic field that is applied across the D's, and it's always perpendicular or right angles to the velocity. So that's what keeps the force, keeping it in a circular motion or in a centripetal motion. Right, so that's why we said we're going to start looking at circular motion equations. Okay, we just said the velocity increases. Okay, because now if you look at our equations, F equals BQV, is what we said now. Circular motion, so F equals MA, or F equals MV squared over R. So now what I have is BQV, so V is capital V for my voltage, equals M little v for speed squared over R. So remember we said it's getting accelerated each time, every time it passes through those D's, so its speed increases, and if the speed keeps increases, So we can see then that the R must keep increases. So if we look at that, R must equal to mv squared. No, I'm talking rubbish, sorry. It's not a capital V. F equals BQV, so our two V's cancel. So what I have is R is mv over BQ. B is a magnetic field that we said was uniform. Q is the charge of the proton. M is the mass of the proton. And because all of these are constants, we can see that the radius is proportional to the speed. So as we keep increasing the speed, the radius keeps increasing. Okay? Okay, so one more time, let's go through that just to make sure we're good. So we'll go from here. So we said F equals BQV, that's speed, magnetic field, charge, speed, equals mass and acceleration, mass V squared over R, okay? So clearly now I have my two V's can cancel because speed on one side can cancel the speed on the other. So I have magnetic field times charge equals mass times speed over the radius. So my radius must equal to the mass times the speed over the magnetic field times the charge. So the mass of the proton is always the same. The magnetic field is uniform. We said it's uniform and passes up for the cyclotron. And the charge of the proton is always the same. The charge of the proton is 1.6 times 10 to the negative 19. So we can see that the radius is directly proportional to the speed. And because our speed is increasing, because we're accelerating it across the D's, our radius keeps increasing. Okay? So knowing that, can you figure out, or can you show me that the speed that the protons come out at is this? So what math are you going to do? So again, it says it's 0.28 meters in diameter. So we know the diameter is 0.28 meters. The magnetic flux density, B, is 1.1 Teslas. And we're trying to show the speed. So I want you to calculate the speed knowing this information. So hopefully everyone right now is thinking F equals BQV, which we know is circular motion, mv squared over R. We can cancel our two V's to have BQ equals mv over R. I want to find V, so V is going to equal BQR over M. I'm in the way there of that, so that's a shame. So V equals BQR over M. So that's what we're using right now. So B, magnetic field strength we know, it's 1.1. Q, the charge of a proton. Remember, protons have a relative charge of +1, which means that protons got a charge of 1.6 times 10 to negative 19. R is our radius, giving you diameter, and mass is there. So hopefully you're thinking now, to find the speed, I just have to do B, 1.1, times charge, 1.6 times 10 to the negative 19, times by the radius, and this is where a lot of people got stuck. The radius is half the diameter, so it's 0.14. And we have to divide by the mass of a proton, because it's a proton that's inside our accelerator, is 1.67 times 10 to the negative 27. And when you plug that math in, hopefully you get a final speed, and you can pop in the chat what you get. So you get a number very close to 1.5. Chatterjee, what's the crack? The video. So I'm doing filming on, I think I'm doing filming for TikTok on Thursday. So yeah, I saw your message, so I will get it for you on Thursday. You have right to give me grief if it doesn't come up, if it's not done after Thursday. Okay, how are we feeling? About to be year 13s about this math right here. Do we get speed? 1.47 times, Priscilla, yeah, beautiful. Yeah, good job. So 1.47 or 1.48 times 10 to the power 7 meters per second, which we can show is equal to 1.5 times 10 to the power 7 if someone wanted to write it to one decimal place. So approximately equal to 1.5. Chatterjee, there was no Key Stage 3 lesson this morning. It was year 12 this morning. You got that, Omar? Yeah, fab, good job. Okay, so now I'm just going to rub out this stuff so we can do the last question before we tab out. So the last question is then, can you now that we have its speed, you just calculate speed, can you now calculate the maximum kinetic energy in mega electron volts? So what's the maximum kinetic energy in mega electron volts? So we're doing part B. What's the maximum kinetic energy in mega electron volts? And then we'll tab out. So hopefully you're thinking kinetic energy, I know from GCSE, is a half of the mass times the velocity squared. I've given you the mass of the proton, 1.67 times 10 to the negative 27. Claire Walker, 14.7 million, 14.7 million. Yes, beautiful. Hello, Claire. Thank you for saying hello. Yes, perfect. 14.7 million is the same thing as it'd be the same thing as 1.4 times 10 to the power of 7. Yeah, beautiful. No, you're right, Claire. That's right. Look, so 1.48 times 10 to the power of 7 is the exact same thing as what you got. So what you got, 1.4 times 10 to the power of 1.48 times 10 to the power of 7 is 14.8 times 10 to the power of 6, which is the same thing as saying 14.8 million. You probably just don't have your calculator in standard form. You're right. Okay, for this one, so we know the mass, you just found its speed. So I got 1.48 times 10 to the power of 7, but it depends how you typed in your calculator. Maybe you got 1.47, that's fine. So what is that kinetic energy? And your answer being joules. Once you get it in joules, you got to put it into electron volts. And then once you have it in electron volts, you got to put it into mega electron volts. Oh, Chatterjee, yes, you're right, 100%. So now you're just joining some year 13 lessons as well. You're going to overwhelm yourself with physics if you try to join 2 harder lessons. But good on you for being motivated. 1.13 times 10 to the negative 24 is what you got for mega electron volts. So Priscilla, when you did this math, so we popped in V, remember it has to be squared. So I got my kinetic energy to come out as 1.83 times 10 to the negative 13 joules. Celine, beautiful, happy days. Yes, I got the same as you, 1.14 mega electron volts. Yeah, good job, brilliant. So electron volts, so do you remember the equation E equals VQ? Energy equals voltage times charge. So energy is measured in joules. If we use the charge of a single electron, that's where it came from, EV. So 1 joule is equal to 1.6 times 10 to the negative 19. Because E equals VQ, we use the charge of a single electron. So that's why a joule, to put it into electron volts, to get from a joule to electron volts, all you have to do is you divide up by 1.6 times 10 to the negative 19. So you do 1.83 times 10 to the negative 13. Divide it by an electron volt. So you divide through by 1.6 times 10 to the negative 19. Electron volts comes up in paper 1, but I can't remember where. I think comes up in photoelectric effect. Did you do photoelectric effect? So 1.6 times 10 to the negative 19. So when you divide that through, you probably get a number of 1143,115 electron volts. But then to put that into mega electron volts, you just have to divide through by 1 times 10 to the power 6 to get it into mega electron volts. Priscilla, good on you, so good. Nalia, beautiful, yes. Omar, beautiful, yes. Yeah, happy days, that was good. Chatterjee, I'm really happy to hear. Hopefully you end up doing the full GCSE course next year, the year 11 one with me. But if you don't, yeah, like 100%, I still use TikTok and Instagram. Perfect. So how do we find, so hopefully we're all going to watch the Free Body Problem, but the year 13 lot, how did you find it? What do you think about cyclotrons? And the other one we were going to do today was the mass spectrometer. But we'll leave it with the cyclotron for today, and then hopefully if you choose to do the full course, we'll go into a mass spectrometer a bit more. I didn't want to rush you through the lesson because again, I didn't teach you guys, right? So it's a bit different. So I guess like now I don't know what you know, right? I'm trying to figure out every day how good our math is. But in a full course, because I'll be teaching you twice a week for a month, I'll know really quickly how much we can put in a lesson because I'll know how fast you all work, right? You do a mass spectrometer chem. Yes, So we do mass spectrometers in physics as well, so we have it here. And it basically it's just making sure you understand about circular motion again, about how magnetic field, as long as always as something is moving, the motion is perpendicular to the force, or the motion is perpendicular to the magnetic field, you always get a force pulling in a circle. And that's why what we were going to do here was this question, was we saw that the proton then will move in a circular path. The proton will move in a circular path because it'll have a force always pulling towards the center of that motion. Okay, so there is homework as normal, so it'd be good if you guys keep trying it, and the video solutions for you guys to watch. And yeah, please give us a like and subscribe to the YouTube. Let us know how you did. Give us reviews in TripAdvisor. Tell me what you think of it. If you think it's helpful. And yeah, remember just as well, if you don't end up coming to my course next year, you can always just watch the go to TikTok and we do past paper questions, and you can always message me. So some people send me messages on TikTok to say like, hey, can you help me with this question? I couldn't do it. And then the next week I try to get to it and do a post of it on TikTok. So say you do a question in class and you have no clue what to do, you just send me like a quick message on TikTok, and then if you don't know how to do it, there's probably other people. I just turn my mic off. How long has that been off for? Hopefully only a second. Was it off for ages? Was I just chatting? Anyway, what I was saying was, like, if you hopefully end up doing the full course, but if you don't, there's TikTok. So if there's a question you don't know how to do, or like a past paper question you want help with, you can just send us a message, and then hopefully by the next week I can do a video on it as well. So yeah, it's just helpful for you guys to fill me in with how you're doing. Yes, Chatterjee, I've got a meeting, but I can stay for like another couple of minutes, so that's good for you. Even you do 6 A-levels. Chemistry, physics, math. What's at HL? What does that mean? Then econ, English, and Japanese. Wow. Even where do you want to go to uni? Damn, bro, that's a lot. I agree, Omar. International Bachelorette. Oh, because it's less exams, isn't it? So there's a little bit less content in the physics. Yeah, so I can stay on till roughly about 10 past, Chatterjee. But just before, probably at 9 past. So even do you go to uni in the UK as well? Nana, have a lovely rest of your day. Hopefully I see you guys on Thursday. So Chatterjee, get your parents to chat to the tech team. Remember, there's like that big they're giving you a 40% discount, like. So get your parents just to call in before that runs out, and like they can talk to them, right? There's no harm in having a conversation. Omar, have a lovely day. Thank you for logging on, and thank you guys for being active in the chat. And Chatterjee, I know Laura was telling me you're in her biology classes as well. So she's another one, can give you another point of view as well. We talked to her about it on her lessons. So yeah, you guys are free to go and have a lovely day. Chatterjee, yeah, sure, I've been replying to your TikToks. I don't go on it, so it's a bit different. Like, so Instagram, I would go on every day because I grew up with Instagram, right? So it's just like, it's kind of like a habit for me to just go on Instagram now every day. But TikTok, I didn't have growing up. So I have to remember about TikTok. So I don't go on it every day. I probably go on every other day. But yeah, I have been replying to you. Did I reply to you today? I think I did. Yeah, but I don't give out my mobile number. You like my glasses? Thank you. My ma actually picked them. So yeah, I don't actually have to wear glasses all the time, but I got to wear them from certain screens for a long time, especially with the bright lights, you know. But yeah, my ma picked them. Zoya, see you later. Have a lovely day. Thanks for saying bye. So, Charity, I gotta go in like a minute. Was there a question you had for me? Astrophysics, because it's what you want to do at uni. I loved it. I did. I do think you gotta be so. I love physics, right? I think it's amazing. I just think you gotta find your niche. Okay. I loved studying astrophysics at uni because I thought it was fascinating. So I love learning about space. I love learning about stars. I did a bit of geology, so we studied about the conditions inside planets. I did planetary science, but they are quite different. So astrophysics is just looking at data from stars. So for example, one of the things I did was that there's an orbiter that's going around Mars. It's called the MRO, the Mars, I can never say the word right, Mars Reconnaissance Orbiter. And what it does, it takes pictures of the surface of Mars. So one of my projects was I worked in a computer all day and I would get the data, so the pictures would get sent to my computer and then I would analyze the pictures to see is there water on the surface of Mars. Another thing you do, but that's more planetary science, right? So that's when I did my master's, that's planetary science. Whereas astrophysics is more that you get, so I thought astrophysics was when you go to travel the world, you go to all these different telescopes and you look through the telescopes with your eye and you look at the stars. And I thought that was amazing because I thought I'd travel to Chile, I thought I would do all that. But now, because technology is so advanced, which is amazing, how it works is you sit in your lab and you learn how to code. So a lot of astrophysics is coding. So you'll send codes or coordinates of the star location or of the region of space that you want to look at to the telescope in Chile or to the telescope that you want to use. And then that telescope the code will telescope where to go, where to look at, and how long to look at it for. And then that data will be collected and sent back to your computer wherever you're working at. So astrophysics is amazing because you think about it like black holes, you're thinking about how the universe is born, are stars moving away from us at a constant rate, are they accelerating? And we know they are accelerating now. We don't know what dark energy and dark matter is fully yet. So there's a lot of stuff unknown that's really fascinating, but you just got to be ready that it is a lot of coding on the computer. So if you're very happy with coding and you're very happy with being on a computer a lot, it's definitely a great career. And it's really interesting for uni. But a positive of astrophysics is because it's such a hard topic, right? Loads of different jobs recruit from it. So for example, lawyers now recruit from physics degrees because you have to have more analytical thinking in a physics degree than you do in an English degree or you do in a lawyer degree. Or if you think about finance and you think about like Deloitte or think about PwC, those big accountancy firms, again, having an astrophysics degree is not holding you back from someone who has a finance degree from applying for those roles as well. So it's definitely a university or it's definitely a good choice for a course at uni if you're still not really sure what you want to do because so many different jobs will recruit from it. On the microphone. Yeah, Charity, just again, hit me that. So you sent me a message about, I think it was Transformers and TikTok. Send me another message about that so I remember to do it for Thursday. Michaela, the last part about mega electron volts, you mean? Yeah, so I'll just rub it out so it's, oops. Oh, can I rub it out? Yes, I can. I'll just rub it out here so I can do it again for you. I hope, Michaela, do you mean the orange part? So again, can I go over part B again? I'm a bit stuck on the conversion from joules to yeah, okay. So you might have did it when you did photoelectric effect. So I don't remember doing like photoelectric effect when you do waves in paper 1. But in paper 1, what you learn is E equals VQ. So energy, which is measured in joules, equals voltage, V times charge, okay? And then because we're always dealing with such small numbers, right? So when you looked at that final number you got, so when you calculated kinetic energy, you find a kinetic energy which was 1.83 times 10 to the negative 13 joules. Because we're always dealing with such small numbers, that's why they came up with electron volts, okay? So an electron volt is just a way of us writing those small numbers easier, okay? So an electron volt is the energy when an electron gets accelerated for a potential difference of 1 volt. So again, electron volt is the energy when an electron gets accelerated for a potential difference of 1 volt. So that's why our voltage, our potential becomes 1 volt. The charge of an electron is 1.6 times 10 to the negative 19. So an electron volt is the energy when an electron accelerates from a potential of 1 volt. So that's why we can write that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So we write things in electron volts when we're trying to represent the numbers easier because it's so small. So to get into electron volts, you go this way. So to get into electron volts, you divide by 1.6 times 10 to the negative 19. So if that's our number in joules, to get it into electron volts, you divide by 1.6 times 10 to the negative 19. So when I do 1.83 times 10 to the negative 13 divided by 1.6 times 10 to the negative 19, you'll get a number in your calculator of 115, and that's in electron volts. But then because I asked for the final answer in mega electron volts, remember mega is a million, so what you have to do is divide that number by a million, divide by 1 times 10 to the power 6, and that's how you get 1.14 mega electron volts. Because remember what that really means is 1.14 times 10 to the power 6 electron volts. Let me know if that's all right. Bye, Shaq. Compare the microphone and loudspeaker, tell me formats. Chatterjee, come to the GCSE lessons, woman. Michaela, is that good? If we are good, I'm probably going to tap out now. So yeah, Chatterjee, just give me a message on TikTok and I'll try to get one done. But yeah, that's more of a GCSE one. So the GCSE lessons, I can cover that. Yeah. Michaela, are we good? Hopefully we're good. Okay, well, thank you guys. And I hope you have a lovely day. Chatterjee, I told you I got a meeting woman. Right, hit me with the next question. But if it's a GCSE question, it's going to be GCSE content, or I'll try a TikTok on it, okay? Part P again. Chatterjee, you weren't in the lesson, woman. But if you watch the video again, right, it's all online. You can watch the video again and it'll all be there for you, okay? But again, I know you're really trying to get ahead and stuff, but once you got your GCSE content down, then you can push the A-level stuff, right? Because they are quite different. GCSE physics is very different from A-level physics. A-level physics is more like math. Yeah, this is year 13, remember, you were in the last year 12 lesson. Right, I'm gonna hit the road. Have a lovely day. Thank you guys. See you later, Chatterjee. See you later, everybody else.